Hello everyone, I'm with you in this video for lecture 18, first part. So this video is about power series solutions near an ordinary point. Up to now, we considered linear equations with constant coefficients, but in general, a linear equation doesn't have to have constant coefficients. It may have variable coefficients. So consider a second order linear equation. So the most general form is going to be some function p of x times second derivative of y plus another function q of x times the first derivative of y plus a function r of x times y equals some function f of x. So here we consider y as a function of x. Instead of t, we use x. Now, in general, such an equation, in general, it is very hard, it is difficult to find an explicit solution. All right, now, if you think about why we want to solve a differential equation, we have this function y of x, and the differential equation gives us, because we have information about how the derivatives of this function behave with respect to the variable x, we construct our differential equation. Then what we want to do is, using some initial conditions, we want to estimate how this function behaves for other values of x. So basically, the reason we are trying to solve a differential equation is in order to find or estimate, if you cannot find explicitly, at least estimate certain values of the function or the general behavior of the function for other values of x besides the initial point. So if it is not feasible to find an explicit function solution, then we try to use other ways and other ways to define a function. And one way is to give the Taylor series expansion of the function. So we try to find the Taylor series expansion of the solution around, remember, for Taylor series, we need a center point. So Taylor series around a given point, x0. So what we try to do, we try to write our function y as an infinite sum, and from 0 to infinity, some coefficient an times x minus x0 to the power n. So the first term, when you take n equals 0, x minus x0 to the power 0, we always take it to be 1. So first we have the constant a0 plus another constant a1 times x minus x0 plus another constant a2 times x minus x0 squared. So it keeps going like this, infinite sum, Taylor series. I am not going to give a review of Taylor series here, or power series, Taylor series. You can find it in the lecture notes. I'm going to share in ODTÜ class lecture notes of Özgür Kişisel from last semester. So here I'm going to continue working with this series. So find the Taylor series means finding the Taylor series means determining the coefficients an. We are going to do this by plugging this form of y into the differential equation, ordinary differential equation. So given the differential equation, we consider y and the point x0, of course, and we consider our solution y in the Taylor series form, like this, and we plug this into the differential equation. We know that we can differentiate a power series term by term, so we can find the first derivative, second derivative, and substitute into our equation to determine the coefficients. But first, we need to make some definitions. Okay, so first, we write the equation in the form we need the coefficient of the highest derivative of y to be 1. So we divide by the function p. So qx over px y prime plus rx over px times y equals fx over px. The reason is the existence uniqueness theorem about linear equations. In order to use the existence of solution, we need the coefficient of the highest derivative to be 1. That's how the proof works. So when we are trying to find a solution, we always try to write our equation in this form first. Okay, now in order to have a solution around a point, these functions need to be continuous, differentiable. In fact, differentiable, I think, is enough. But they need to have, they need to behave nicely around the point x0. We know that if they are not continuous, for example, at the point, then we cannot guarantee the existence of the solution around that point. So first, we recall a definition. Well, maybe you, in your calculus course, you didn't use this name. So in this case, okay, maybe instead of recall, let's say definition. Let's define it here. Probably you've seen it in your calculus course, but okay. A function f of x is analytic at a point x0 if we can write our function as a Taylor series expansion, for x in an open interval around x0. So this means we take the point x0 and we find an open interval centered at x0. So this is this number here is what we call rho, if you remember from calculus course, the radius of convergence of your power series. And this has to be a positive number. So there must be some open interval. And we take all x in this open interval. And this number rho is, remember, is the radius of convergence of the series. In other words, we can also rephrase this theorem as f of x has Taylor series expansion in some open interval centered at x0. If you remember from calculus, this is not always true. Even if you have an elementary function, and even if you have a Taylor series which converges in some open interval around x0, it may not be equal to, the Taylor series may not be equal to the function. So this really defines something new. Not all functions behave like this, okay? I'm not going to give you the example. This is done in calculus. But again, it's in the review in the lecture notes. So if you are curious about that, you can read the lecture notes. Okay, so another definition. In order to write a Taylor series expansion of our solution, we need the coefficient functions to be analytic at the point x0 so that we can attempt to find the power series solution. So we say that a point x0 is an ordinary point of the ordinary differential equation pxy double prime plus qxy prime plus rxy equals fx if the functions qx over px and rx over px are analytic at x0. We don't, okay, assuming that the functions are analytic is much more than the assumption of the existence uniqueness theorem, because existence uniqueness theorem just says continuity of the functions and also the function on the other side of the equation. I'm sorry. So this is, to be an ordinary point is much more than saying that that the conditions of the existence uniqueness theorem are satisfied. This is much more. So when we have an ordinary point, as you are going to see in the examples, it is going to be very simple to find the Taylor series expansion of Taylor series expansion of the solution of an ordinary differential equation, linear, in this form. Okay, so what if the point is not ordinary? In that case, we call it singular. Otherwise, x0 is called a singular point. Okay, so I'm going to give you examples now about how to find series solutions around an ordinary point. So the first example, find a power series solution of the equation second derivative of y minus x times y equals 0 around the point x0, which is 0. So first we need to check that x0 is an ordinary point. So in our equation, the function px is 1, the function qx is minus x, I'm sorry, this is Rx. Qx is 0. Rx is minus x. Fx is 0. So Qx over Px is 0. Rx over Px minus x. Polynomials. So these are analytic at 0. If your function is already a polynomial, it means it's itself. You can consider it as a power series with only finitely many terms. So all polynomials are analytic. And in this example, we have polynomials. All polynomials are analytic at every point x0. So in this example, the coefficients are polynomials, so they are analytic at x0. So this means we can try to write our solution as a power series centered at 0. So some coefficient an times x to the n. Let me remind you what this means. A0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4, and so on. Okay, now we are going to take the derivatives and substitute into the equation. So what is the first derivative? So the first term in our expansion is constant a0, so its derivative is 0. So the first term of the derivative is going to be a1. Derivative of a1x is a1. Next term is 2a2x plus 3a3x squared plus 4a4x cubed, and so on. So in the summation notation, since the first term is constant, when we take the derivative, the new sum is going to start from 1 to infinity. We have the constant an, then derivative of x to the n is n times x to the n minus 1. And if you substitute the values of n, you see you get this expansion above. And similarly, for the second derivative, again, the first term in the expansion here, again, first term is constant. So when you take its derivative, the first term is going to disappear. So the sum now going to start from 2 to infinity, a n times n constants, then derivative of x to the n minus 1 is n minus 1 times x to the n minus 2. So the first term is 2a2, and then 3 times 2a3x plus 4 times 3a4x cubed, and so on. Okay, now substitute into the equation second derivative of y minus x times y equal to 0. I'm sorry. Oh. Okay. So second derivative of y, let me take the left side of the equation first. So the second derivative of y is the sum n from 2 to infinity, n minus 1 times a n x to the n minus 2, minus x times the function y. For the function y, we take this Taylor series expansion, n from 0 to infinity, a n x to the n. So next step is to combine the sums. Next step is to combine the sums. So we need to do some manipulations first. First of all, we have x times the series, so let's take that x inside. The first sum stays the same. And the next sum, I take the x inside, I multiply all the terms of the sum with x, so x to the n becomes x to the n plus 1. To combine the sums, the first thing to do is to make the powers n. So get x to the n by shifting the index. Look at the first sum, n starts from 2, and the power of x is n minus 2. Making this power to be n, it means shifting the index by 2 units up. That means shifting the starting point of your index 2 units down. So in the first sum, instead of starting from 2, you start from 0. And inside the sum, instead of n, you're going to use n plus 2. So a n plus 2, and this is going to be x to the n. So maybe recall, if you have n from 2 to infinity of a n x to the n, then when you start n from 0, you shift the index inside by 2 units. Okay. So this is what I used here. For the second one, same thing, but now in the other direction. The power of x is n plus 1, so I need to bring this 1 unit down. So I take the initial index 1 unit up, and from 1 to infinity. Then inside, instead of n, I use n minus 1. So that gives me x to the power n. Okay, now both sums have x to the n. Okay, but the starting points are different. The first one starts from 0, the second one starts from 1. So the first one has an extra term for n equals 0. So that term I write first. This has extra term for n equals 0. So let's write that term. What is the term? If you take n equals 0, n plus 2 is going to be 2, n plus 1 is going to be 1, n equals 0, so n plus 2 is going to be a2. So we have 2, a2, and x to the 0 is always 1. So the first term for n equals 0 is 2, and the rest of the series now, n starts from 1. And we have the second sum. Okay. So this 2a2 is the term n plus 2, n plus 1, a n plus 2, x to the n for n equals 0. Okay. Let me continue here. So 2a2. And now the two sums, they have the same x to the n and the same initial point. So I can combine the two, n from 1 to infinity. Since x to the n is the same in both sums, I take it out. In the first one, the coefficient is n plus 2, n plus 1 times a n plus 2, minus, in the second sum, the coefficient is a n minus 1. Okay. And remember, so this is the left side, y double prime minus x times y. We write it as the constant 2a2 plus the sum n from 1 to infinity, n plus 2, n plus 1, a n plus 2, minus a n minus 1, x to the n. And in the differential equation, remember, the left side is equal to the right side, which is 0. So now we have this sum equal to 0. Think about this sum as a polynomial. So for this polynomial to be 0, it means all the coefficients must be 0. Okay. So let me write this down. So for the sum 2a2 plus n from 1 to infinity, this thing, whatever it is, times x to the n, to be 0, all coefficients of different powers of x must be 0. So we have the constant term 2a2, that has to be 0. And then this coefficient, remember this coefficient is n plus 2, n plus 1, a n plus 2 minus a n minus 1 should be 0. But remember, this is for n greater than or equal to 1, because in the sum, n starts from 1. So this coefficient is for n greater than or equal to 1. So for n equals 1, we have coefficient of x. N equals 2 gives us coefficient of, so maybe I should write this down. N equals 1 gives coefficient of x. N equals 2 gives coefficient of x squared. N equals 3 gives coefficient of x cubed, and so on. All of them has to be 0 because we have the whole sum equal to 0. All right, so we have, from the first equation, we have the number a2 equal to 0. So the coefficient a2 must be 0. Then for the other equation, we solve for a n plus 2. This is equal to a n minus 1 divided by n plus 2, n plus 1 for n greater than or equal to 1. So this formula is called a recursive formula. This is a recursive formula. For a n plus 2. So we try to write all coefficients a n's in terms of the first two coefficients, a0 and a1. Because we need, for recursive formulas, we cannot solve them explicitly. We need a starting point. For the starting point, we need two coefficients, a0 and a1. Okay, so we have a0, a1. We already figured out a2, that has to be 0. Now, what about a3? So let me call this formula star. For a3, use star with n equals 1. The formula star is valid for n greater than or equal to 1 anyhow. So the first valid value is n equals 1. So n equals 1 gives on the right side, on the left side gives us a3. On the right side, we have a0 divided by 3 times 2. So a3 is a0 over 6. Now, for a4, we use star with n equals 2. So a4, the left side for n equals 2, the left side gives us a4. The right side gives us a1 over 4 times 3. Okay, so let me see if I should keep the multiplied out form. So, okay, let me keep it this way. And let's continue. Now use n equals, oops, I'm sorry, one moment. Star, where's my star? I'm having trouble with my arrows. Okay, so now we use star with n equals 3. So that gives us a5 equals a2 over 5 times 4. But remember, a2 is 0, so a5 is 0. Then a star with n equals 4 A6 equals A3 over 6 times 5. But what is A3? A3 is A0 over 3 times 2. And then take n equals 5. A7 equals A4 over 7 times 6. Now, what is A4? A4 is A1 over 4 times 3. So 7, 6, 4, 3. So we keep going. N equals 6. A8 equals A5 over 8 times 7. But A5 is 0. So you see, we get the coefficients in groups of 3. We have A1, A0, A1, and A2 is 0. Then we have A3, A0 over 3 times 2, A4, which is A1 over 4 times 3, and then A5 to be 0. And then A6, which is A0 over 6, 5, then we skip 4 because A5 is 0, 3, 2. Then A7, A1 over 7, 6, we skip 5, 4, 3. Then A8 is 0. And then we will repeat. This pattern is going to repeat itself. So we are going to get terms in groups of 3. Okay? So the solution, remember, y is A0 plus A1x plus A2x squared, A3x cubed, and so on. So A0 plus A1x, A2 is 0. Then for A3, A0 over 3 over 2, x cubed. For A4, A1 over 4 times 3, x to the 4, A5 is 0. Then A6, A7, and A8 is 0, so it will keep going like this. So we are going to have terms with A0 and terms with A1. So if we group them, terms with A0 is going to be 1 plus 1 over 3 times 2 x cubed plus 1 over 6 times 5 times 3 times 2 x to the 6. And the next one is going to be 3, 6, 9, 9, 8. We skip 7, 6, 5. We skip 4, 3, 2, x to the 9, and so on. And then we have the terms with A1. We have x plus 1 over 4 times 3, x to the 4, plus 1 over 7, 6, 4, 3, x to the 7. So the next one is going to be x to the 10. So 1 over 10, 9, we skip 8, 7, 6, we skip 5, 4, 3, x to the 10, and so on. Infinite sum, of course. So this A0 is like the constant C1, and A1 is like the constant C2 in the general solution of the differential equation. So the function, the infinite sum in front of A0 is our first solution, 1 plus 1 over 6x cubed plus 1 over 6 times 30, 6 times 30, 180, I think, x to the 6, and so on. And then the next we take the function in front of a1, x plus 1 over 12, x to the 4, and so on. So these are the two independent solutions. Of course, for solutions, we just give their Taylor series expansion around x0. Okay, I'm almost out of time for this video. In the next one, for this lecture, in the second part, I'm going to give you another example. So just let me point out, general solution, a0, y1 plus a1, y2. Or if you want, c1, y1 plus c2, y2. Okay, until next time.